just machine data. There's things we kind of do for machine data to work with that particular set of data. However, sequence analysis can be applied to a broad spectrum or broad set of different classes of data. And so what I'm going to attempt to do is kind of go through how these techniques are both used on the machine data sets that we have today, but also are leveraged for things like predicting poker hands in a poker data set. So given somebody's betting patterns and sequence of betting patterns, can we classify or predict what hand that individual is holding because of those sequences of actions? And the reality is, we're really just talking about sequences of actions. And sequences of actions happen across the board. When we think about machines, so clouds, right? We've got data centers across the world, all over the place. And we've got lots of servers across multiple racks. So we've got monitoring aspects in each one of those things. Every second, what's CPU at? What's disk at? Pings replying? What's the ping latency on these servers? Just to kind of keep the health of the overall being of the data center alive, right? And I like to kind of break it down into verbs and nouns. So when we think about sequences, there's generally a noun and then there's generally a verb. And so in the server case, the server is the noun and then the action would be the monitoring of that particular entity. So you have a server and then there's an action which is CPU changes, or there's an action which is disk changes, or there's an action which is a ping response happens. And so really we just have nouns that have verbs acting upon them. And the same thing happens in poker. We have a verb which are actions people are taking. So we have betting actions against certain players. And, whoops, I skipped over 2 things. So breaking down kind of what am I going to be talking about in this particular talk. So just going to go through a quick meta philosophy around data, because I kind of believe it have some sort of philosophical point in the ground that helps you model the world. And having that philosophical point in the ground actually helps you kind of become a better data scientist, because you just have a certain frame in which you view the world, and you kind of try and structure most of the problems that you work with in that particular frame of reference. I'm going to be talking about generalized sequences and their applications. I kind of went into that, going from poker to machines, trying to kind of show two completely different spectrums of data sets. I'm going to talk about blended HMMs, which is kind of a technique that I've been using on poker analysis. I'm an avid poker player, guilty, as well as in machine stuff and machine data. So that goes into kind of pattern detection, smoothing techniques, and then how we use a little bit of recommender techniques in time series analysis. So just a quick show of hands, how many people are at least familiar with HMMs? How many people have actually really used an HMM? Okay, good, so hopefully we'll get something on this. And so that's a good demographic sample for objective of this talk, because really all I'm trying to do here is pique your interest and get you thinking about analyzing sequences of information and structuring data in such a way that it actually is a sequence of events. Help you figure out where to start. So in other words, if you have a particular problem case or have particular ideas about data sets that you have, and as you hear me talk, you say, hey, you know what, I think we have a data set that looks like a sequence, or maybe could be finagled into looking like a sequence. How do I start analyzing that? But I also want to kind of help understand the versatility of HMMs and their applications. And I think HMMs are a very popular technique in text analytics. So you see them, kind of their standard use case is around part of speech tagging. But in reality, HMMs can be used for a variety of things outside of just part of speech tagging. And so I'm going to be talking kind of about how you can use them from classification all the way to segmentation and clustering if you really want to. It's a little bit harder to use them as clustering, but it actually does work. So what's my meta philosophy on, yes?
What does HMM stand for?
Sorry, thank you. Hidden Markov model. So A Markov process you can think about as a series of events that happen. And these are things you can see. And so in a Markov process, you can think of things like any game that gets played that has events which happen that you can see, everything is in front of you. So like chess, there are sequences of actions that have a certain probability for that action happening. And a Markov process is simply, you have a series of actions and we call that a particular state. So after you've made an action, so I've moved pawn to 2 places forward. I'm now in a new state. I was in a previous state, and now my game's in a new state. And so these games move from state to state, and we call these state transitions. And so as these transitions are happening, the probability in which you move to a different state changes. Now, that's a Markov process. So the hidden part of a hidden Markov process is sometimes you don't actually know, you don't have information about you. So in the case of poker, actions are happening. So I see like people are betting and raising into a poker chip pot. But the information I don't have is I don't know what is driving those actions. I can see some information about the cards on the table, but they're holding 2 cards in their hand for which I cannot see. And so that is the hidden part of a hidden Markov model they call these hidden states. And so you can think of like the starting hands in poker. So I should stop. Sorry, I have ADD, so I kind of jump around, so bear with me. How many people are familiar with poker and how to play like Texas Hold'em and that whole kit? Oh, awesome. Okay. Good. So the hidden part is you don't know the whole cards, right? And in a hidden Markov model, we try and make inference on, okay, given these action sequences, what is the most likely state in which this person is in? And those states actually end up being the whole cards. Yeah. Sequences are good because we can find abnormal sequences. And so this is a screenshot of something we did in our intelligence.rackspace.com product. But starting with the general question of, can we identify servers that need extra attention from our support floor? Because what's happening is, now going back to kind of sequences of actions, right? So servers are nouns and there's actions happening on these things. And we have a state of known normal behavior in various servers and in various poker hands and whatever. There is a state of kind of known normal behavior of what's happening. Now, if we start analyzing those sequences and we start coming up with sequences that are deviating from outside of what we believe to be a normal sequence, we can start flagging those things as anomalous and say, hey, this is a weird looking thing. Now, anomaly detection in this state is actually a really challenging problem. So if you go into anomaly detection, there's kind of, especially for this kind of problem, and so this is very early days for these kinds of things. But in anomaly detection, you have kind of 2 core problems that you need to solve. One is just the identification of what is anomalous. So this is just snapshotting what the actual identification is. And so, things for which normally have kind of a linear upward trend that all of a sudden fall off, that don't normally do that, we can flag as anomalous, and that's an identification. Now, the crux of actually making anomaly detection very useful, and this is the hardest part, is what's called the relevance problem of anomaly detection. So you can go identify anomalies all you want, and they are anomalies because they are outside normal behavior. However, they cannot be relevant. And so having feedback loops into anomaly detection of determining relevancy of is this anomalous or not, and was it relevant, are critical. So as you're kind of Googling around anomaly detection and various terms for these kinds of things, Google about those 2 core crux problems in anomaly detection, and you'll find research papers and whatnot to ramp up on. But the 2 core problems to think about there are the identification and the relevance problem with it. But really, we're more so trying to kind of get this kind of information to make recommendations and suggested troublesome servers to have a look at. So the reality is, when you take these kinds of things, further forward, you start building services that kind of make these things live. So in other words, hey, you give me an account ID of a particular person, and I'm going to suggest servers that we should go look at because they're deviating outside the norm. Okay, so I'm going to go into and start breaking down kind of hidden Markov models and what they're all about, and how we start doing real things with them. So up at top here, I think, okay, animations are gone. I'm not a PowerPoint engineer. These are what we consider the hidden states, so x1, x2, x3. And so we're kind of modeling kind of two core things in this whole sequence. So as you can see at x1 here, there's a probability that x1 moves to x2. There's a probability that x2 moves to x3, and vice versa. x2 moves to x1, and really x3, x2, they didn't have an error there. Then we have this layer right here, so this red layer, which is what I call the inference layer, but I think that's made up. But in essence, that's kind of what we're trying to do. We're trying to kind of, and these are the observations that we can see. So we're trying to kind of take observations which we can see, and these observations have particular sequences about them, right? And so as we look at the sequences of, okay, y1, 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 y2, y2, y1, y2, y3, y4, we can see there's a behavior happening. And the reality is these behaviors are being driven from some layer in which we can't see. So what we do is start trying to make inference about, the current state that we're in and the hidden layer that was perhaps driving that behavior. And I'll keep driving down into this stuff. So, but why Markov models? So why do we use these kinds of techniques? Why do I like these kinds of techniques? I think they're very simplistic, yet adaptive. So they're kind of within the family of belief networks and Bayesian networks. And they're kind of one of the most naive approaches to them, but it's a great starting point because they help you get from 0 to like 75%. But then once you start needing to make further optimizations, it starts getting harder and harder. But the reality is to kind of get it from the 0 to 75, which is I think most of it, because you spend the 80% of your time, of course, everyone's heard all the statistics, munging the data, and then you're just like, okay, I just want to get from the munge data to something that like is real and works, and just want to be done. These can help you out there. They're very adaptive. So in other words, it's there's not a whole lot. I mean, there is. I shouldn't say this, but I'm going to say it anyways. There's not a ton of maintenance like you would with parametric modeling, where you pick these variables and pick these parameters, and then you have these scoring systems on the back end where you got to rescore them, and then maybe one of your parameters doesn't work anymore, so you got to find a new variable to go in and fix it. Markov models can be set up in such a way that they're reasonably adaptive, because really all you're doing is as this data is coming in from x1, x2, x3, and you're kind of observing the different state sequences down here, all you're doing is updating probabilities to two different matrices. And so, a hidden Markov model is essentially just two matrices underneath the hood, but they're probabilities. And so as different things are happening, you just kind of keep updating these probabilities, and so the model kind of evolves with the work that you're doing. They're very flexible, so they solve a multitude of different problems, so you can actually use them for classification. If you just give them all the data of one of the labels that you're looking for, I want to go find ace king. You give it all the data with ace king, it's going to come back and learn a set of parameters, and then you just use those set of parameters in your other HMMs to start predicting if someone's holding ace king or whatever. You can also use them for clustering. So that's a supervised approach where I'm saying, like, actually, I'm kind of cheating because I can see these things now. And it gets a little confusing because you're just like, well, Nick, you just said, like, they're hidden, you can't see them. And, well, yes and no. So there's a class in game theory where we call this perfect recall. Or not, I wouldn't say perfect recall, but we have recall, which means there's a state in which we can't observe, but in a future state in time, we can observe it. But you generally call it hidden Markov model from the point of reference in a current time slice, which is right now. So right now, no, I can't see these things, but I can actually go back through my history and learn from my history so that we can kind of make these hidden inferences later on. They're a reasonably scalable approach. Now there's some aspects that aren't scalable, but in terms of the prediction of them, once you have your two matrices, the Viterbi algorithm, and I'll go into kind of Viterbi after this, is highly parallelizable. And the other major thing is temporal. They're very good with repeat patterns, and so in a lot of the data that we deal with in our machine-generated data, we have a lot of temporal effects. As you can imagine, like there's various time periods where servers get used a lot, there's various time periods where servers are not used a lot, and various time periods where things are more memory constrained, but it all depends on the application that's running on the different servers. And so we see, and of course like Black Friday, like all the e-commerce crap turns on and bandwidth is all over the place. So a lot of models don't necessarily model that temporal effect. But in some of the stuff that we deal with on a regular basis, the problem even further complicates when in like economics, we have seasonality effects. So it's just, we have various quarters where we know they're down periods and it happens relatively consistent, so we can normalize on dates of, okay, on this day and this month, like we can, normalize and adjust the trend and smooth it here. But those are known fixed points in time that we know about. And in some of these temporal sessions that we get is a problem I call kind of unstable periodicity, where you do have periodicity, so there is a cyclical pattern, but at which point in time that cyclical pattern comes is random. And so HMMs are reasonably adaptive to temporal effects in time series. And so let's kind of start diving into what are HMMs. And so the crux of the whole shenanigans that we're talking about here is you have visible observations that are dependent on the hidden states. And so the dependent part is critical. So you have various hidden states, but the whole reason that we can start making inference about what those hidden states are is because there is some dependency. And that dependency is a lag one, what we call lag one dependency. Yeah?
Is there a place where the presentation is kind of difficult to follow along because it's a little hard for us to read?
Oh, sorry. No. Sorry, I probably should have put this out somewhere. I'll try and read everything on the slides as we go through. But that dependency is critical because what we're saying is, and it's a lag one dependency in Markov models, but because you have a lag one dependency, the previous observation helps predict the next. And because we have that dependency, we can start making these inferences. There's three core components to HMMs. So there's a forward-backward algorithm, there's a Viterbi algorithm, and a Welch algorithm, and I'll go into each of these in more detail as we go. And under the hood, everything sounds so complex. We've got Markov processes and hidden things that we can't see, and Markov models. And the reality is, like, when we talk about a model, everyone kind of thinks of models as these magical, mythical things. Models are just equations, but in HMM world, well, they're equations too, but the essence of them, the meat and guts of them are matrices. So you have two matrices. You have a transition matrix, and you have an emission matrix. And all the transition matrix is saying is that we're talking about the probability of transitioning from one hidden state to the next hidden state. The emission matrix is the probability of going from a hidden state to an observation. Now remember, the observations are the things that we can actually see. And so when we talk about, so we're going to talk about forward-backward algorithm right here. So it's the first of the three components. This is kind of the workhorse of HMMs. And the forward-backward algorithm answers the question, what is the most likely state given some time t? So I'm in some time t, and what is the most likely state given I'm in some time t, and we've accounted for all past previous history. We use this to kind of start making inference. So you can think of the forward-backward algorithm as the thing that goes through, and as actions are changing, it's going through and updating all the probabilities based on these historical actions or in present state action. There's two parts to it, the actual algorithm. So there's the forward and back. There's the forward part, which is, again, that probability of a state given a sequence of observations. So in other words, I have a sequence of visible observations, a list, and I want to compute the probability of a state given these are my observations. There's the backward part, which is exactly the opposite, hence backwards, but it's the probability of a sequence of observations given you're in some state. So given I'm in this state, what's the probability that this is the actual sequence? And so what you kind of keep doing this in the Welch algorithm. And so here's just so you can kind of see what's going on. This is some toy code for the actual forward part, but I tried to kind of explicitly comment things and show kind of how we walk through this. But as you kind of implement some of these algorithms, these are all the input parameters. Actually, how many people are kind of like engineering, have coding-ish backgrounds? Okay, so we can do this. So you have your input parameters to the actual function, right? And so we give it a list of observations. Again, this is a list of things that we can see. We have a list of states, and this is a distinct list of the actual different states. Now and we can't see these things, right? So you're just like, well, what do I put here? You actually just give it an arbitrary number. But it's not really arbitrary. You kind of use some of your domain knowledge about the particular problem that you're trying to model and solve to put your best guess of a number in what this thing is. So an example might be if I was trying to kind of, if I was looking for something very simple on like a trend, and I want to kind of smooth that trend out, but I want to smooth it out in a very, very mundane way. I might pass an HMM to it and say, you know what, go find 3 states in this trend. And I set states to 3, and that's it. And it's an unsupervised problem, so it's going to go through these things and just come back with, well, here's a bucket of 3 things, and here's all the time points within this trend that I've placed into these 3 different buckets. And depending on kind of how you set up parameters, it can come back with high, low, and no change. And that's entirely unsupervised. So, I mean, the uninteresting part is like, well, yeah, like we could just use the tracking to go solve that. The reality is, like, you didn't tell it anything. You just said 3 things, go find 3 things, and I'm not telling you if it's high, low, or negative, but it can pull back what is high, low, and no change. And so this kind of just goes through and computes the actual probability of the states given the sequences. And essentially what you're doing, and this is kind of that whole dependency part, we have a list of posteriors, and we just take the first element, multiply it by the previous element, and that's your dependency of that one lag dependency. And so the interesting bit with these things, and there's not a lot of work and implementation out there, but once you kind of understand these parts, it's relatively easy to change these things and make them do whatever the heck you want. But where this starts to get interesting is you can easily modify this and say, you know what, I don't want to do a lag 1 HMM, I want to do a lag 5 HMM. And so you simply just kind of go back, lag 5 in the posteriors and the transition probabilities, and you can kind of add whatever lag periods you want and start building some models on, I'm not just going to look at the past element, I'm going to look at the past 5 elements and compute probabilities based on those past 5 elements. And this is the backward part. I'm not going to step through this just because it's exactly the same. Not exactly, but it's just reversed from the forward part. And then the whole last step is once you compute the forward probabilities and the backward probabilities, you literally just go through and blend those together to produce the probability of state given some sequence of observations. Okay, so we'll go into the Viterbi algorithm. And this answers the particular question of, given an HMM, what is the most likely state sequence? So this function, you give it an HMM model. So you give it the transition and emission matrices. And then you say, okay, what is the most likely state sequence given this thing? And it will go through and kind of map your 3-state each time point. It will return to you a matrix the same length of the data set that you gave it. So you can just column append the output of states to whatever data set you gave to the Viterbi algorithm, and you have your state mappings. And this is kind of how you can start using them for clustering and whatnot and different techniques, because you're saying, okay, unsupervised, let's go find 5 buckets. So you could conceivably use them to kind of bucket customers and say, you know what, I have behavioral actions from the clickstream on my website that people are clicking over here and they're looking at these products, and these products we know are high value things, and we want to start bucketing these people into various behavioral buckets. You can give them, yeah.
Quick question, taking a step back. How do you define sequence?
It's a good question. I define sequence as a sequence needs 2 things. It needs a noun and a verb. And the actions have to happen in chronological order. And that's a very important thing. So it's an entirely abstract notion and probably need a better definition for how we just define these things. But the reality is, if you have some non-action item, some noun, and some verb acting on that noun, and these actions on that noun are happening in a chronological order, and not necessarily time related, but it's just, if one event happens, the next event is the next sequential logical movement. And that forms a sequence. So the reality is, sequence really are a very, very broad term. So the whole idea of Viterbi is really just attempting to find causation of the actual observations. And that's those hidden states. So we see these states and there's something happening to them. How do we go find what is potentially a cause? And having the state doesn't actually give you the causation, so I probably shouldn't say that, but I do that a lot. But what it actually gives you is a place to kind of start looking. So if you can start bucketing things into a state 1, state 2, state 3, state 4, you then can start plotting these things and looking like, okay, what is in this bucket of 1? What did this thing, just in an unsupervised way, like I didn't tell it anything, it's just a little baby that we're kicking off into the world and it quickly learns things. What did you go put in state 1? Then there's the Welch algorithm. And this is just a variation of expectation maximization. So there's a very famous EM algorithm, which is what a lot of models use to kind of learn various parameters. And Welch is just a variation of expectation maximization. And so what this does is you give it a sequence of observations, and it gives you what a good HMM is, which is awesome, which is why I love this so much. Because it's just like, it essentially kind of helps you build a model for you. So you don't have to go through and build a bunch of models. You just hey, Welch, here's some observations. What are the good parameters I should put in this thing? And it comes back and tells you what those parameters are, which is awesome. And so how it does this is it just leverages forward-backward algorithm. You give it some convergence criteria. And it goes through, and once the emission and transition probabilities in the two matrices stabilize to some convergence criteria, so in other words, they're not moving very much anymore, so no matter what we're doing to this thing, we keep pumping observations through, and we keep running forward-backward algorithm, and we keep updating these things. And we're not changing the probabilities, they're just kind of staying fixed. It stops and says this is the most likely model for these observation sequences. Which is great, so it builds your model. So how can we use them? We kind of went through a lot of these, but they can actually be used to kind of smooth out time series. So in other words, if you give them various parameters about a particular time series, not just a single sequence, this would kind of have to be a multivariate Markov model. But if you have extremely highly volatile time series, you could actually say, you know what, I'm going to give this time series a 6 state HMM. And my 6 states are super low, kind of low, medium, kind of medium high, and it actually can chunk it out and model the series based on those different levels. And so now what you've just done is you've reduced an extremely noisy sequence into a much more manageable state sequence. Because once you map those different states, you're just using the actual number values that the state maps to, and you can normalize on that, and you have a reasonably smooth trend. Talk about number 2. I don't know what number 3 is. I probably would put that in here on some other talk, and somehow made it in here. I have no idea what that means. Number 4. You can give it the HMM plus the observations to Viterbi and actually go calculate the sequence, which is what we went and talked about. And so, smoothing techniques. So what do we talk about when we say smoothing? Is everyone familiar with like smoothing techniques of various trends? Okay, cool. Oh, yeah. Google terms. Always look for those Google terms. Smoothing techniques are when you have like extremely volatile, and this isn't even like super duper volatile. I think this is like some stock chart. But you have a time series which has a lot of up and down stuff going on. And the reality is like you don't really care about all this variation going on. Like we call from here to here variation, right? And so we have a lot of variation in this sequence here. And the reality is that we don't care about that. Like we just want to get the general behavior of what this thing is doing. So we use a series of techniques called smoothing to try and reduce variation in trends before we actually go analyze them. So you don't want to go analyze a raw time series on stocks without kind of reducing that variation. And you can imagine, memory and CPU on computers is far worse than the stock market. Like that CPU is like always jumping to top. It's on. It's like over here. And so you're like, well, I don't really care about that. Like I just want to get the general behavior of the actual CPU. And so you use smoothing techniques to kind of smooth out those trends to just capture the essence of, okay, here it's kind of going down, it's kind of going up, it's kind of going down, it's kind of going up. And the overall trend is kind of down on this thing. And so these things are kind of useful, like especially if this was like a hard disk graph, because you're like, actually it would have to be inverted the other way. But that's okay, still the same thing. Hard disk is going on where they're writing files, they're not writing files, they're writing files, they're not writing files. And if this is inverted, we would see an upward trend. And so we know that there's a limit on hard disks of, whoa, you've only got 100 gigs, and we're trending towards that 100 gigs, and the trend's moving at this kind of acceleration, so we can kind of forecast out that in like 5 days, we're probably gonna run out of disk space. So smoothing in time series is just like any other data set where you generally don't want to use raw data when you go feed an algorithm, right? You make some feature to it, you normalize it, you change it, you manipulate it, and smoothing in time series is one of those ways where we kind of change and manipulate data to do whatever we want. And the overall objective of smoothing is really just to uncover the true behavior of the trend. So within the volatility, there is a hidden, not really hidden, but there is a behavior going on, and we just want to capture the essence of what that behavior is. Like, is it going up? Is it going down? Is it happening on this time period every time? We just kind of want to find those things. And so here's some various techniques for actually doing some smoothing. So you have moving averages and running medians. And I would just write these things down, or I'll send out these slides. And these are just Google terms, right? So like as you're researching these things, like Google these things. Like that's basically the point of this slide. There's exponential moving averages, which just kind of has an exponent to the actual time series. There's differencing, which helps you. Differencing is just like, so if you did a lag one differencing, you're just saying subtract the current state from the previous state, and what happens is you get a magnitudinal change. So if you care about magnitude of the trend, just take the current state, minus whatever the previous state was, and differencing will give you what the magnitude change was. And then there's the autocorrelation functions, which help you kind of uncover periodicity in the actual trends, which kind of show you what these functions, you basically pass it to series, and it goes and tells you like, okay, these particular time periods are actually correlated. And it will show you nice little spikes of like, yes, this is very correlated. No, it's not very correlated. So challenges in smoothing trends. So again, we have kind of that periodicity stability problem, where especially kind of in machine data, we have highly volatile time series, and there are intermittent periods of cyclical behavior. So it's not, Black Friday, you're gonna get a lot of traffic, and you know it, right? So that's a cyclical seasonal pattern. But with this, the time point and when the cyclical pattern starts and stops is unknown. And so that makes it extremely hard to kind of smooth these trends. But HMMs help us kind of identify some of that unstable periodicity. Again, these are super hard problems, they're unsolved. If you're super smart and want to solve them, come talk to me. And in a lot of these kinds of things, we can use recommender techniques in the series, and it looks like some formatting, wonderful stuff going on. When you reduce the states into a vector, so this is a vector of states, so state 5, state 1, 1, 1. You can start defining a similarity function. So now you have a vector of particular elements, which are the state sequences. And so now I can start doing things like, okay, here's a completely reduced vector of what this series actually is, and we reduced it into 5 states. You can start doing things like trend-to-trend similarities and recognition. So once you reduce the series down into a much more usable trend with an HMM, we can start mapping those states into similarity functions. So like if you just do like a cosine similarity across the 2 vectors, you get a certain similarity score, and then you sort them by, okay, which trends have good similarity scores. You can see it completely captures the essence of the behavior of this trend, right? So these are 2 completely different trends, and these ended up being servers that were actually part of the same application base, right? So they're behaving very similarly, but not in the same way, and so we can start doing things like machine grouping for states that we don't know, and start getting a better understanding of what behaviors are coming out of various applications. So again, in my mind, the application is the hidden state. So we've got a lot of things running on servers, but we don't know what applications are running. But if we kind of start, we don't need to actually know the application. We just need to know what states or buckets of applications are driving various behaviors of servers, because then we can start further optimizing on how we treat those applications differently, maybe giving them more network bandwidth or what have you. The other thing we can start doing with this is once you have a known state, so let's just assume this was some failure trend, right? So it looks like it's got some super high acceleration, and acceleration is just the rate of change in the actual trend, right? And so this looks like it's accelerating rapidly. So we might just say, you know, we know this, like we know servers do this, or we know this behavior exists. So as you go look, I just don't know how to work this. Okay. So as you go look through the 2 million servers that are out there logging these trends, look for this trend. And so you can use these, you know, HMM plus similarity approaches to say, I know what I'm looking for, and it's this. Go find me all the trends that actually look similar to that. I can come back with it. And so the actual problem landscape that we have is questions of like, can we identify poker hands based on betting sequences? Can we identify servers? Can we identify applications based on their monitoring activity sequences? Can we find groups of similar behavior sequences to identify action buckets associated with the behavior? So this is going on to things like customer churn. So I get a lot of conversations with, you know what, like we know churn looks like this. Like a lot of companies like have a particular behavior pattern of like, okay, everyone's super jazzed about what's going on, and then it kind of peters off, and then maybe it kind of pickers up a little bit, and then it takes off, and then it just drops. And so we know that trend, like. And other companies know these kinds of trends for like what this is, right? And so, and you can start using these groups of similar behavior sequences, you can start identifying these kinds of things before they actually start happening to kind of build a more proactive notion of, okay, we know what churn looks like, we know what application state sequences look like. How do we treat things differently given we know these things beforehand? That's a note to self. Okay, walk through code examples. How are we doing on time?
You have an hour.
Okay, cool. Okay, so this will be. How are we gonna do this?
Grab a chair if you like.
That's a good idea. Okay, there's no like prereq, you don't need to have anything installed. This will be like super ad hoc moment of the workshop. So I'm going to kind of pull up some code samples and show you kind of how I'm using HMMs in poker and in machine data, and let people ask questions. You're welcome to kind of go, download R onto your computer and kind of like zone out and start looking at, there's a package called DepMix S4 if you want to download it and start working through some of those tutorials and examples. You can go do that and ask questions. I'll kind of go through some of these code examples, but if you want to kind of get hands-on and start seeing like, okay, while he's here, I want to download this thing and see if I can't get an HMM that actually does something. Let's go for it. So my screen not. Yeah, I'm going to figure out how to get not that on, and then I'll write it down.
You just do Windows key and P. It should let you select whether you want to hear it or choose a different one.
Okay, nice. Yeah, cool. So, for those who kind of want to follow along, can everyone see this, or let me see if I can zoom in? So that's what we zoom in. Can you guys see that URL, or no? No, you can't, because I can go see it. Well, here we go. So just type this into Google. Everyone see that? Yeah. So just type that into Google and start downloading it. And really that's just the name. So like inside your R console, or R, if you have R open or whatever, just install .packages string detmix s4 and it should install. You should be ready to go. And then if you just look at, obviously the docs, there's a data set that they have already, like in the examples, and like anything, the first thing to do is like just, I guess my particular style when I'm kind of trying to ramp up on something new is like just download it and see if you can get it outputting something, and that's it. Like, don't try and like understand everything that's going on, but just like get the thing to output a thing, and then you start figuring out if the thing that's being outputted is actually like what you're looking for, and then you kind of quickly iterate from there. So I think success in this session is I'm going to go through stuff like you can tune in, and I'll show you kind of like how to get super deep and super advanced with build an HMM model and then use it to actually train another HMM model to go predict poker hands. But as all this is going on, you can kind of look at my code and just try and get some examples working, and then I'll be walking around, and anyone who has questions and whatnot afterwards, we can just kind of take it as a study hall hours after I kind of go through some of these code examples. So let's go through the ontology of the actual function. So the main function that you want to care about is detmix. And so although it's called detmix, it actually is an HMM. It's just mathematicians and statisticians like to do these things where they call similar things very different things, and the reality is the same thing. So detmix is dependent mixture modeling, and dependent mixture modeling is actually hidden Markov model, disguised as a different name. And the reason it's called dependent mixture modeling in this particular package is it's a superset of generalized linear models. And so the main difference is, again, I'm going to keep harping on that dependency thing. So in a generalized linear model, it makes the assumption that the sequence of things that you're looking at, or the data set of things that you're looking at, has no dependency. So this observation doesn't mean anything about this next observation. So once you add that dependency term, you now have a dependent mixture model. Otherwise, you just have a mixture model. And so a dependent mixture model is pretty much exactly a Markov model. And so the main function to care about in detmix, the S4 package, is this detmix. And so detmix enables you to actually go create an object of a hidden Markov model. So let's go through here, and real time take you through kind of what you're likely to just do at home, but have somebody talk you through it so you don't have to read hours of documentation. Did I skip it? It's like right at the top. There we go. Okay, detmix, found it. 4. So here's the parameters. We'll talk through. Yeah, so touchy. Okay, so this creates an object of HMM. So remember, HMM is really just a transition and emission matrix, right? And so this is the object, so we're not doing anything like learning the parameters or whatnot. We're just defining, this is the structure of what the HMM thing looks like. And so you give it a response, which is a model for the various things that are actually in, this is your observation of sequences, essentially. And so the nice thing about this particular package is if you look at a lot of the HMM implementations out there, this is the only one that I use that I've seen that actually has a multivariate HMM. And what I mean by multivariate is you can have multiple variables in the actual successive sequences versus, so like, you know, Python's scikit-learn and a number of the other HMM implementations out there are very rudimentary and very basic in the sense that they're just operating on single sequences. And so the nice thing about this package is if you have multiple observations, so I have CPU, RAM, memory, disk, these are multiple variables in a sequence. And so they all happen at the same time points, but it's all, you know, a single multivariate sequence. This allows you to analyze that. And so then there's a data element. That's pretty straightforward, no mistakes. Again, this is just kind of like an arbitrary number you get to go put into the actual function. But you generally use this, so how do you think about you know, what number of states do I give my HMM model? You generally think through it in terms of, there's usually something you're trying to find when you go cut an HMM loose on a thing. And so like in the poker examples, it's, you know what, I'm looking for starting hands. And I'm really just looking to differentiate between, do they have a pocket pair? So that like in their 2 cards that they get in Texas Hold'em, if you're not familiar, you know, do they have 2 cards the same? So are they playing this hand like a pocket pair, or do they not have a pocket pair? And so that's a 2-state HMM in that realm. Now, another state HMM would be like, what you're saying to the HMM is, okay, I'm going to give you 2 states, and I'm going to set up the input parameters of the actual model to try and learn what those different states are. And if I was looking for something like, well, you know, I want to try and see if we can find suited connectors, pocket pairs, and then everything else. That's a 3-state HMM. And you say, okay, input these observations, these multivariate variables, and I'm going to give a 3-state, and we're going to see what comes out. And that's the general gist. And so this family option, so as you're using this, family is the distribution of each of the different variables that you're putting into the actual HMM. So if we go back to the code, and where's that defined? Actually, it's called this. There you go. Yeah, it's not one points for scrolling. Okay, so we look at this. This model parameter is that response parameter. I just call it model to make it more confusing on everyone. You know, I'm modeling so this is a multivariate HMM, and I have 3 different variables. And this family option is just telling the HMM, there's 3 variables, variable 1, variable 2, variable 3, and they have a multi-nominal distribution, which is just a superset of a binomial distribution, where in a binomial distribution, you just have a random subsampling of 0 and 1. In a multi-nominal, you just have a random subsampling of n possible classifiers. So multi-nominal, if you're familiar with kind of R and whatnot, is essentially a factor. So, you know, as dot factor in R would map to this multi-nominal distribution. The other option is, you know, like in the server data examples, you know, any sequence of numbers you generally model as a Gaussian. And so, you know, the beauty of you know, HMMs and their flexibility is, you know, we're just defining these distributions, and this package just has these distributions implemented. But if you had other distributions of data that you know about, you can add those as features into an HMM and just say, you know, this isn't Gaussian or multinomial, it's Poisson, it's, you know, Dirichlet. It's whatever distribution, you can model it as such. Okay, so that's the main function. So I'm just going to give you like, the two main functions to like really care about and focus your time on as you're learning these things. And then the other one is the fit function. So just walking through what we're doing with these functions. So depmix defines the object, and then fit helps you optimize the parameters of the object, right? So if you're going and learning these things at home, these are really the only two things to go focus on. Is the fit function and this depmix function, and you'll be off and running HMMs. I might go get my mouse because I'm just failing with this mouse pad. Sorry, let me quickly get my mouse. Oh good, I left it in the speaker lounge. Okay, I can do this.
Borrow one?
I have one USB port. It's being used.
Oh, okay.
This is a Bluetooth one. That's okay, I'll use touch screen.
Can you make the PDF one?
Oh yeah, sorry. Okay. So fit. So, fit does two things. So fit is your forward-backward algorithm, and fit is your Viterbi algorithm. So back to the slides. The HMM object that you go and define, the actual model is the depmix function, and then the fit function is your Viterbi and forward-backward and Welch algorithms. So you get all three in one kit, essentially, which is great. It makes it very easy to kind of use. These things. So going back to how we actually use these things, if we go into, I can remember. So this is the general sequence of how you use these things. So you create ignore the create blended because that's an advanced topic. But essentially what you do is you define a depmix function and pass it the parameters of how you want to start the initial model. And you can even, just to get your feet wet, just give it randomized parameters, and it will do that. You just say, okay, here's a data set, and then make your initial probabilities, make your transition probabilities, make everything 50%, which is basically just like start off completely random guessing. Yes?
So, fundamentally, I was trying to understand this. So if you have only a fit function, where is the prediction piece of all this? Is the fit is the prediction itself?
Fit has the prediction wrapped in. So if you use like the GLM functions in R, so the general sequence is, make a GLM function, fit it, and then call predict on the fitted GLM function. This fit function has that wrapped in it. And so what it does is it maps it computes Viterbi, and then it gives you a vector, which is the state sequences. And that vector matches the actual row length of your data set.
And the sequence. So
Yeah.
what you're trying to predict is the sequence, because that is what it is.
Yep. And then all you do is append that onto the data set.
So like GLM, classic GLM, right? You have a training set and then a test set and then cross validation. So nothing like that we do here.
Yep. So you do that, but you don't have to do the testing So like if I break it down like this, so like there's train, testing the actual model. So in other words, train the data or train a model, check how well the data fits the model you just trained, and then validate that what you've trained actually works on the data set, right? So that would be the train, test, and validation. The Baum-Welch or the expectation maximization algorithm actually kind of takes care of the whole testing parameter of how well does this model fit this data. So I generally just break it down into, I have a training data set and then I have a validation data set. So I give it my 60% training data set, I train that HMM, and then I use those parameters in another HMM object and say, okay, when you compute Viterbi, use this, so that it's doing that prediction on a completely different.
And my final question is, if I understand the sequence, that's what I'm trying to predict, how does that help me from the machine intelligence aspect? Because I understand the sequence, but I'm more interested in the result. What is the result of those sequences?
I don't think I understand your question. So are you,
So I understand the sequence of activity, because that's what I'm predicting,
yeah.
right? So I'm really to understand how does that help me in terms of solving the machine intelligence problem.
I see. So those, so in terms of like, can you define the machine intelligence problem that you're talking about? So like, is that,
So overall objective is for me to look at my IOPS, look at my CPU, look at my memory,
yeah,
eventually figure out whether, or in one case, figure out whether I'll have a failure on that particular box or not,
yeah,
right? So that's the result that I'm interested in.
I see.
With SMM, the way I understand the sequence of activity, what I understand is what sequence of activities are in the middle of the process, which is getting explicit to me. So how does that help me understand whether there will be failure or not? So what I'm really interested in is that this particular box, will that fail in 10 days, 15 days, or 20 days? That's how
So I would say that that particular problem set is like a classification problem.
exactly.
And there's two ways you can go about that. Like you can go the whole random forest route and everything. How you do that in the HMM sequence world is you would train an HMM. You'd not do the whole random subsampling and then pass that to random forest or pass that to logistic regression or whatever. Is you'd just segment the data set. You'd say, I know what all the failures look like, and here's the data set where I've, in my where clause, I've said where failure is 1, and here's all the past behavior sequences. And then I would take those sequences and just give them as that's the only data set you give the HMM. And you say, learn these things. And so what it will do is take those behavior sequences and then come back with, here's a transition and emission matrix that best describes the failure data points. And so then you take that transition and emission matrix, and you might just give it a 2-state HMM in that problem. And state 1 might be the actual failure state. So then in your next HMM, and let's say you have more states now rather than just failure, but you just learned failure and what that looks like, and you hold that state fixed. This is kind of like the advanced HMM topics, other than it's actually easier to do them unsupervised, but if you want to get them to do classification, this is kind of how it works. You hold that state fixed in your new HMM object, so you give it not just the failure data, but the non-failure data and any other data you have. But you say, as you're updating these probabilities, don't touch this state, because we already know what it is, and hold it fixed. And so then all of your classifications will end up in that particular bucket. So now how you get to the actual, how you get to prediction of, will this fail, is a much harder problem. I don't think the problem is actually, I think I think it's a reasonably unsolvable problem to really predict and forecast out. You know, in 3 days, this is going to fail. But you can, what you want to do is identify it as fast as you humanly possibly can. And so you need automated approaches to the identification of that. The prediction of it, it needs to be a very well-baked problem, you know, like disk trending or any other things like that, where simple logistic regression can go predict like if the disk is going to hit the thing. Yep.
So is it fair to say that the two matrices are roughly equivalent to, in the typical R model, the predict object, the model object that you?
Yep. So you can think of Viterbi as your predict function. So, however, I don't like calling Viterbi predict because it doesn't actually predict, it just maps. It maps states to the actual sequences. Because keep in mind, like we're not trying to predict like some future state with Viterbi. We're just trying to say we don't know what these states are and we want to map them to some real result. And so in you know, linear regression and logistic regression, we're generally trying to predict, okay, this, you know, trend is looking like this, and how do we forecast out, you know, 10 time periods forward. HMMs don't do that. You can actually make them do that, but it takes some serious manipulating in the gut work. What they're really good at is when you have these sequence of observations and you're not trying to, it's prediction in some sense, but it's not prediction in some forward time period.
It's prediction like the clustering.
Yeah, it's prediction like in a clustering, but you can use it like prediction because what happens is when Viterbi goes through, it computes a probability for every state, and then all it does is max. It takes the max. It says, okay, I'm going to go through all the states and compute all the probabilities, and then we just take the highest probability. So the probability that I'm in state 1, and we might have mapped state 1 to, you know, poker hand ace king, and probability at this point in time t that we have state 1 is 80%. And so we can be reasonably confident that that might be ace king. And so that's kind of how they work. So I wouldn't think of them like, you know, if we got to do some forecasting into the future, you're using a different model. I wouldn't use HMMs. Yeah.
I have a question. So when you have these inputs, these called exogenous variables, these multivariate problems,
Yep.
they're influencing the outcome, and they're trying to smooth them, their input. So
Yep.
you have this variable. In essence, aren't you doing like a remodeling of these time series to get them smooth properly? Because if you don't, you might not get a good answer if you're in the Markov
Yeah,
model.
it's a similar, I would say it's a step before you might go do something like arena or whatnot. It's like I've seen people that do smoothing techniques with like k-means. So they'll smooth a series with a k-means function and then pass that into an arena model. But I don't do a ton of arena modeling.
But
and
in the end,
whatnot,
those
so-
are techniques that are particular to arena. It's like, because
Yeah,
it's a time
totally.
series. So you're trying to find a stationary trend in there, a stationary series, I should say, so you can feed it properly. Because if you don't, because I'm concerned that if you don't find a good smooth series, could your final answer not uncover it? I mean, would you have difficulty, if you don't want to get rid of that excessive noise, with some type of smoothing?
For the particular use case that we have, in just identifying similar trends, it doesn't matter so much because all you're kind of trying to do is get that behavior characteristic to find, you know, are they behaving and moving in a similar state?
But if you have so much noise going on with all those variables, it's difficult unless you do a real modeling first and the influencing variables. Just a thought.
Yeah, it works. Okay, so screen. Okay, so we got our fit functions. Step through that, and literally it's an easy call to this once you kind of define. The upfront part is really just defining and getting the right parameters to depth mix, and then all you do is you literally just call fit on the actual object that you just created, and what it does is it goes and maps Viterbi. So I'm gonna see if I can SSH into this box, but like a cooking show, I've already pre-canned everything because it takes a little while to run. How are we doing on time? Okay. And so I'm just going to kind of walk through the various objects that. Everyone see this? Okay-ish. Let's see if we can zoom in more. There we go. Oh, I got two screens. This is the right session. I got two servers here, so it looks like. Okay, so going back to code. At the very top, we'll kind of walk through the output of these things just so you guys get an idea of what they spit out and how to use it. But if we look and let's go inspect one of the objects. So this was a very rudimentary model I trained that was just looking for ace king, and so in an actual poker hand sequence. And so if we look at the output of DMM, this is what this is the output of when you call det mix. This is the output of what it actually gives you, right? And so you have two initial state probabilities, which we can see are just, basically saying like, hey, start out guessing and converge and continue optimizing and re-optimizing. And then you have the transition matrix, and again, this is, from state 1 to state 1, state 1 to state 2, and again, it's all 50%, like just guessing. And then we have three variables, so multivariate, and within each variable, it's just starting out as zero coefficient. So like we're literally saying like this thing's super dumb, like doesn't know anything. And if we then look at, after we call the fit function, you'll get a fit object. And fit has a lot of goodies inside of it. So you've got the transition densities, you've got the response coefficients. So if we just dig into this response object, looks like I don't have enough screen space for that. But what I did was I essentially just said, you know what, let's spoon feed it. Like it's a super dumb model. Let's spoon feed it. Let's give it all the ace kings that exist in the data set. And let's give it all the 7 deuce offsuit. So those not avid poker players, 7 deuce is the absolute worst hand. And ace king is reasonably good hand. And so the reason I did this is because it doesn't know anything. So if it starts to learn something, I can give it a 2-state HMM, and it should likely be able to divvy out which one's ace king and which one's 7-2. Because I'd imagine everyone's not playing their 7 deuce. So this is just kind of like, think of this as like, okay, here's what's going through Nick's brain when he chooses state to this model. And so as I'm kind of doing this, it's like, okay, I would imagine not everyone's playing 7 deuce like they are ace king, and if they are, they're probably not winning. So if we just give a 2-state HMM, these two hands, I'm reasonably confident it should be able to kind of come out and map them appropriately. So let's check. So in that object that we have that maps, oops. I have another object in here which is aggregation of all the different states. So this is a custom function that I've implemented that makes these features super easy to access. But if we look, it actually doesn't get anything wrong in the first pass. So it mapped everything to all 1,000 7-deuce offsuits to the right state. And how you know it starts getting things wrong is I might have, 100 7-deuce offsuits in state 1. And so like, and I'll show you kind of like as we increase hands, it starts getting fuzzier. Then you start getting other hands ending up in the different buckets. But the reality is in this pass, because we chose 2 completely different dynamics of betting sequences, it actually gets them right. And so all the ace kings ended up in bucket 1. But the nice thing here is because we spoon fed it, we now know, like we've got some good parameters for ace king. And so what I did next was I then took those parameters and trained another HMM, but said, we know what ace king looks like. And so as you're engulfing all these other poker hands, what does ace king look like? And I guess we're doing a lot of poker right now, but this is all the same thing. I guess the message I'm trying to show is that we're doing machine translations and machine state analytics the exact same way we're doing kind of poker stuff. So the only difference is the states that we're analyzing on the machine data sets is they're just different states. So we're looking at applications, so we don't have visibility into that, and we want to know what applications are going on based on the machine behaviors, right? And the challenge is that those data sets are massive. So just and I was working on this, but I was not confident that I'd be able to kind of do Hadoop clusters and all sorts of other things like in real time, so I wanted to downsize data sets. But the reality is we've got just a 1-month sample was over 7 terabytes of data. It was actually 80 terabytes of data. So it's kind of like, this is a much downsampled problem than what we deal with. But, okay, so let's say, so now that I've taken kind of those ace-king parameters, so like, okay, we know what ace-king looks like. Let's go make another HMM, and instead of giving it 2 hands, I'm going to give it 5 hands. I'm also sticking with poker because everyone kind of knows about poker. So when we look at, where's my 5 state? This one should be the 5 state. And so if we look at the evaluation matrix, we just gave it 5 more hands, and it still gets it right. So it maps state 1 is all ace king, and then it puts everything else in bucket 2, in the 2-state bucket. And so keep in mind, we're just giving it betting patterns. And so the three variables that I'm giving it, and we can map it back into the actual code, is the point in time of the actual flop. So there's pre-flop, flop, turn, river. So there's 4 actions there. Then the next is bet, check, raise, or fold. So there's another, this is a multivariate. So there's 1 variable. The next variable is bet, check, raise, or fold. And then the other is a ratio that I've kind of come up with, which is just, pot divided by bet relative to stack size. Because you don't, and the reason we do that, and then I just chunk that into a 3-state bucket to say it's a high, medium, or low raise, but it accounts in the person's stack size. Because the reason you do that is because some things that look like a very high bet aren't actually a high bet to the person that's got a lot of chips. So you kind of smooth that out, and if you do that in such a way, you can start sequencing and seeing, okay, we know what ace-king looks like, and all we're looking at are betting patterns of those 3 variables of was it pre-flop, was it a bet, check, raise, or fold, and was it a high, medium, or low? And with just those 3 data points, now mind you, I'm not giving it, and this can easily be optimized, but I also wanted to show that I'm not BSing, because as you start expanding more hands, it starts getting fuzzier, and it starts not understanding what's going on. But with 5 hands, it works pretty well. But, and this is kind of like, how I kind of go through modeling these kinds of things is do the dumbest, super simple, stupid things you can first. Just get the things outputting. And so like here we've got a thing that works on 5 hands. But when we expand it to 10 hands, it doesn't quite work so well. So what do you do next? Well, we're only using 3 variables. So I then need to optimize with another variable, but we can very quickly see that the variables that we want to start optimizing for are, I'm not giving it any of the community cards. Like I'm not saying like, this is what the board looks like. Now, based on this person's actions and what the board looks like, what do they likely have? So we can easily start optimizing this super rudimentary model that actually works pretty well on these cases, but I want to show you how it starts getting fuzzy. So if you map states to what the hand is to how frequently it occurs. If we look at the 10, I think I have a 10 state on here, yes I do. That wasn't the 10 state. Okay, so as you can kind of see, now we've got multiple things in state 1. It's not just ace king. But the interesting thing that's happening here, and as we can kind of see as it starts going out, everything that's in state 1 is actually a reasonably decent hand. So the thing that it put in state 1, and this makes sense. So as we start kind of decompressing what's going on here, it kind of makes sense. So we've got ace king in bucket 1, we've got 7 ace in bucket 1, we've got suited connectors in bucket 1, and we've got 3 queen. That doesn't make any sense. Crap. I thought this was the example where, so I must have reran this, but what it did, it randomly samples hands, but the other hand that was in here was pocket 5s. So, but as you go through this, you can imagine, pocket 5s, pocket pair, middle pocket pair, ace king offsuit, pocket 5s, like, I'd imagine there's some, maybe people are raising pre-flop for slow check-in or whatever, but there's going to be similar betting patterns to higher value starting hands relative to the weaker hands. And so what it's actually doing is it just kind of bucketed some of the higher value starting hands. So like the suited connectors, 5, 6, and 6, 7, those are higher value in terms of profit potential. So if you start mapping and looking those out, like they're not, you don't want to go in the, like obviously you don't want to do heads up with those, but in terms of profit potential, like if you hit your straight, if you hit your flush, like you generally make bank. So the higher value starting hands are actually ending up in bucket 1 relative to the rest of it, like jack deuce offsuit, king 4 offsuit, like these are all kind of, junk starting hands and they're all going in bucket 2. But the higher value hands, so we kind of start seeing that it's actually figuring out what the hell's going on. And so we could do the same, do I have the monitor? Yeah, okay, cool. And so we can do the same, same exact techniques mapping back to monitoring. So in other words, I've got metrics happening on servers, and I want to start understanding what server, and sometimes you might not know the server, but I want to know what server those particular metrics are coming from. And so these things have behavior patterns, and this is a little bit harder just because there's a lot more variability, but if we just look at this, that's the wrong one. That's the confused one. I don't know where that one went. One sec. I might be on the wrong machine. I got 2 machines. Oh crap, I'm on the backup machine. That's why. I got two machines running just in case like something worked on one, I could easily switch over to the other one. I don't have all the stuff on the other one. But Any questions on this kind of stuff? Anyone trying to get it working right now?
Tricky without the data.
For the examples, they've got some speed data and whatnot. Yeah.
Out of the data you collected, how much of it do you think was generated by other models, other bot predictive type?
Say that again?
Out of the data that you collected in the large data set, was any of that, or how much of it do you think was generated by other people using some other model like yours in order to play exactly your scale down case?
Oh,
What happened?
I don't know. So that data set that I'm using is actually all just robots.
Sure, it's not.
Yeah.
It is very, it's not.
It is.
It is.
It's not. It's all just a simulated robot environment.
Sure.
Yeah.
How does your model play up against itself?
So I don't have it playing against itself yet, but that's absolutely the next phase.
Yeah, it sounds like a lot of what you're talking about is game theory. Right?
Oh, it's 100%. Yeah.
Oh, cool question. So, is there sort of lower bound on how many states should we have to get some sort of prediction out of it? Is it going to perform well or poor? Or is it going to, or I guess not states, how many events in a sequence do you need? What if you have 6 events that happen? And it's like I'm trying to figure out in terms of machine learning, like you usually have P and N, like you know how many variables you have and how many observations you have, and then you have you need some sort of imbalance there.
Yeah.
Figure out, like you need a lot of samples for a few variables to get some good robustness.
It's the politician's answer is it does depend on the data set and what you're kind of trying to go accomplish, but it generally does need more information and a lot of sequences of actions on particular data sets. So like if you've got small samples and small sequences of information that is happening, so like if you just did a few hundred poker hands, so like if we go back to the poker data set example, if we look at there's 169 different starting hands, and if we look at the distinct, if we just use the variables, the 3 variables of pre-flop state, the action state, and then the size of the bet. You can compute the number of, so I think there's, within each of those, it's 14 possible states per individual hand. And so then that maps into, in your transition matrix, that's 14 squared, because you're going state to state, and that's just that matrix, right? So it very quickly starts exploding, and when you have a very reasonably sparse amount of potential actions, you need a lot of data, because what happens is you need history, like you need recurring things, and if there's 100 million possible different action sequences that can happen, you need a certain number way bigger than that to do that. So it all depends on how many combinations of state sequences you have relative to the size of data you need. So if you've only got 300 million observations and you have 100 million combinations of action sequences that can happen, you haven't got enough data.
Right.
Because it's either bucketed in one, or that's 3 historical things per possible number of states.
Sure.
So you kind of think of it in that terms. Yep. Yeah.
You might have already addressed that, but could you, I think I'm not enough, but all right, so you might actually have addressed that before because it missed half the workshop, but could it be like that there will be multi-layer hidden Markov models?
Yes.
Okay.
Absolutely. And so what you generally do is you use your transition matrix as the starting state for the next hidden Markov model that you use. Right? So if you have a subsample of a data set, you generate a transition matrix that has the probabilities that you're looking for those states. But then if you add more states, you can use that transition matrix as the starting state for a new object. So you say, dep mix new, and then transition equals this transition matrix, and it starts learning from there. Versus in the rudimentary stuff that I showed, it started learning from birth, essentially. I call that state birth, right? It's like it knows nothing. Then it moves into an adolescent phase of, okay, I've learned something, and I'm going to use those learnings, and the learnings is your transition matrix, so just fuck that out and put it into another one. And what you do is, I have a friend that gives me a hard time about this, but I consider this like a deep learning thing, right? Like you get multi-layer in Markov models because you're continuously kind of like getting deeper and deeper and learning new parameters. And so yeah, that's absolutely possible. And they perform way better when you do that. Yes? We gotta go. We gotta stop. Okay. I'll take it off. Okay, go ahead.
I'm not a data scientist, so
Yeah.
forgive me if my question is dumb.
No.
So in your experience, have you ever faced a situation, have you ever run analytics based on from different data sources, like part of it's from machine data, maybe part of it, you blend that with customer demand data,
Yeah.
and to predict machine failures and things like that? Just wonder if there's any real practice on that.
So if there are situations, so like in real practice situations, there are situations where people have, hundreds of thousands of data sources. So, maybe, in email situations where they're, serving out, I was just having this conversation with somebody, but their problem is like they have a bunch of different vendors for like a queuing bandwidth thing. I don't know email that well, but the reality is they have like 100,000, and they have these sequences of actions that are happening. And some of these data sources are actually kind of fraudulent sources. They're spammers, right? And spammers use similar data sources for where their email actions are coming from. So there's these different servers which are data sources, and there's 100,000. And so like depending on who your email hosting provider is, if there's a service that leverages a bunch of different email hosting providers and then kind of pulls that back into one of their own hosting service that just aggregates these things, they want to identify fraudsters, right? So you want to know, well, I've got 100,000 buckets coming from various email hosting providers, and I want to understand which of these buckets is fraudulent behavior. And if you have a known state, and in this particular case they have a known state about what fraudulent activity is happening, you can go train an HMM and say, like, here's all fraudsters, this is what they look like. Do that in a two-state. You're either a fraudster or you're not. Give it a two-state HMM. Take the transition parameters from state 2, whichever the fraudsters end up in, because that will be arbitrarily assigned. So then you just look and say, like, oh, the fraudsters are in state 2. And you can take that, and so that's a real application. Or even if you're just, consolidating a lot of different data sources, and you might not know which ones you have. That's absolutely an application.
Thank you.
All right, thank you very much.